Our universe hides 50 planetary secrets stranger than science fiction. You are about to witness a cosmic tour of the most bizarre worlds ever discovered, from planets of solid diamond to sunless wanderers drifting in eternal night. By the end of this journey, you will see our galaxy not as a quiet neighborhood, but as a menagerie of the weird and wonderful. How can a planet rain molten iron? And what does a world made of cotton candy tell us about creation itself? What do you believe is the ultimate fate of a planet consumed by its own star? Our journey into the cosmic oddity begins not with a star, but with its absence. Picture a world in perpetual midnight, a lonely giant adrift in the freezing gulf between stars. This is PSOJ 318.5-22, a rogue planet. It was discovered not by the dip of a star's light, but by its faint, solitary glow in the infrared. This world, several times more massive than Jupiter, does not orbit a sun. It is an orphan wandering the galaxy without a parent star to give it light or warmth. How does such a colossal world end up completely alone? The leading theory suggests it was violently ejected from its young stellar system, a planet thrown out of its cradle by gravitational chaos. This single discovery forces us to reconsider the very process of planetary formation. It implies that our own solar system's neat, orderly arrangement might be the exception rather than the rule. If one such wanderer can be found, how many more are there, invisible to our telescopes, drifting in the dark? Astronomers now suspect these lonely giants could outnumber the stars themselves, a hidden population of dark worlds threading the galaxy. What secrets of planetary birth and death are they carrying through that endless night? This rogue planet proves that the cosmos holds more than just worlds of rock and gas. Far from that lonely wanderer, another planet exists that is the very definition of opulence. 55 Cancri E is a super-Earth that has turned into something else entirely, a jewel on a cosmic scale. It orbits so close to its sun-like star that a single year passes in just 18 hours. The surface temperatures are hot enough to melt iron, creating a truly hellish landscape. Yet the true wonder lies beneath that scorching surface. Astronomers analyzing the star's composition and the planet's density made a stunning deduction. This world is not made of silicon and oxygen like our own. It is overwhelmingly rich in carbon. Under the immense pressures of its interior, that carbon has likely crystallized. This suggests the planet is in essence a gigantic diamond, possibly mixed with layers of graphite. Imagine a world 3 times the size of our own, glittering with crystalline structures. Its value in any earthly terms would be incalculable, a treasure beyond all human wealth. But how does such a world even form? It requires a stellar system that began with an extraordinary abundance of carbon, the same element found in pencil leads and in us. The raw materials for life under the wrong conditions forged a dead jewel. This diamond super-Earth challenges our assumptions about what is normal. It reveals that the building blocks of planets can vary wildly, creating landscapes we once thought were pure fantasy. What other priceless worlds are waiting to be found, turning our understanding of cosmic chemistry upside down? The diamond world is a monument to pressure, but some planets are forged in pure fire. Co-Rho T7b is a super-Earth orbiting so close to its star that its entire surface has become a global ocean of molten rock. This is not a planet with lava lakes, it is a single, seething sea of magma. The star-facing side is locked in a permanent, blistering day where temperatures soar beyond 4,000 degrees Fahrenheit. At such an extreme heat, the very rocks on the surface do not just melt. They vaporize, sending a silicate mineral haze into a thin, scorched atmosphere. This is where the planet's true nightmare begins. The atmosphere on the day side is so hot it is filled with the gaseous essence of rock, but this vapor cannot escape the planet's gravity. Prevailing winds carry it to the frigid, permanent night side where temperatures plummet by thousands of degrees. Here, the rock vapor cools and condenses. It does not fall as water, it falls as pebbles and stones, a relentless, rocky rain sleeting down into the global magma ocean below. This world has a weather cycle made of geology itself. How do you even begin to comprehend a landscape where the sky rains stones and the ground is a liquid fire? Co-Rho T7b shows us that the conditions on a planet are dictated by one simple, brutal rule. Proximity is everything. A world that might have been a rocky cousin to our own has been warped by its orbit into a vision of pure, elemental fury. What other familiar materials could be twisted into such alien weather patterns across the cosmos? The violence of the cosmos is not limited to single worlds. Entire planetary families can be thrown into chaos, as proven by the Upsilon Andromeda system. This is not a single, bizarre planet, but a full solar system gone sideways. It hosts multiple giant planets, but they do not orbit in a neat, flat plane like the pages of a book. Instead, their paths are wildly tilted, with some orbits angled almost 90 degrees to the others. How could such a dramatic misalignment occur? Our standard model of planetary formation begins with a spinning, flattened disk of gas and dust, with all the baby planets naturally settling into the same orbital plane. Upsilon Andromeda shatters that peaceful image. Astronomers believe this cosmic disarray points to a violent past. The most likely culprit is a gravitational brawl. In the system's youth, one of its giant planets may have been flung into a new, tilted orbit after a close encounter with another. Alternatively, the star itself might have a distant, unseen stellar companion whose gravity has slowly, over billions of years, torqued the entire system out of alignment. This discovery forces a profound realization. Our own solar system, with its orderly and predictable orbits, might be a cosmic sanctuary of stability. The galaxy could be filled with these tilted, chaotic systems, where the gravitational pull of one world can upend the paths of all the others. If you lived on a moon around one of these tilted giants, your night sky would be a constantly shifting, unpredictable map of stars and planets, a celestial dance choreographed by ancient chaos. What other hidden forces are capable of warping a star's entire family of planets into such a permanent state of disarray? While some worlds are forged in fire and molten rock, others are born impossibly light. HTP-1b is a gas giant, a world so inflated it defies the very definition of a planet. This hot Jupiter orbits blisteringly close to its star, completing a year in just 4.5 Earth days. Its size is staggering, over 30% larger than our own Jupiter, yet its mass is actually lower. This creates a density so incredibly low that it is less than that of a cork floating in water. If you could find an ocean large enough, this entire planet would float. How can a world of such immense scale be so lightweight? It is a cosmic balloon, a puzzle of physics. Conventional models of gas giants cannot fully explain its structure. The intense stellar radiation it receives should heat and expand its outer layers, but this alone does not seem to account for its extreme puffiness. Astronomers are investigating hidden, internal heat sources. Perhaps the planet's own gravity is slowly compressing its core, releasing tremendous energy that puffs it up from the inside out. Or maybe its atmosphere is composed of exotic molecules that trap heat with extraordinary efficiency, acting like a celestial down jacket. This puffy planet forces us to rewrite the book on planetary interiors. It reveals that gas giants are not all built the same. Some are dense and compact, while others, like HTP-1b, are fleeting, tenuous giants, their vast atmospheres barely held together by gravity. What does the existence of such a fragile world tell us about the delicate balance between a star's fury and a planet's will to hold itself together? From a planet too light to sink in water, we journey to a world that may be water itself. GJ 1214b is a super-Earth, but its identity is a complete enigma, a featureless orb that hides its true nature behind a perpetual global veil. This world is entirely shrouded in a thick, steamy atmosphere, a blanket of haze so dense that our telescopes cannot see any surface features below. It presents a perfectly smooth, uniform globe to the universe. What lies beneath that impenetrable shroud is one of astronomy's most tantalizing mysteries. The planet's size and mass suggest it is not a gas giant, but a world rich in water. This leads to two equally bizarre possibilities. The first is that GJ 1214b is a true water world, a global ocean thousands of miles deep. Under the immense pressure of such a colossal sea, the water would not be like our own. It would transform into exotic states of matter, perhaps a hot, dense fluid behaving more like a solvent than a liquid, or even a solid, crystalline ice that forms at room temperature due to the crushing pressure. The second possibility is that the entire planet is enveloped in a strange, high-pressure form of water ice, creating a singular, icy crust over a hidden interior. In either case, this world has no continents, no mountains, and no shorelines. Its entire surface is a single, unbroken environment. If you were to descend through its atmosphere, you might find yourself falling endlessly into a superheated steam bath or landing on a surface of hot, solid ice. How does a planet become so uniform, so utterly lacking in the variety that defines our own world? GJ 1214b stands as a monument to the strange simplicity that extreme conditions can impose, a perfect sphere hiding a secret that challenges our very definition of an ocean. This cosmic disarray takes an even more dramatic form with HTP 7b, a gas giant moving in absolute defiance of its star. This planet orbits backward. While its star spins one way, the planet travels in the opposite direction, a celestial rebel on a retrograde path. Such a backward orbit shatters every expectation of how a solar system should behave. In our own neighborhood, every planet follows the sun's spin, a legacy of the swirling disk from which they all formed. HTP 7b's path is a clear sign of a deeply troubled history. It could not have been born this way. Something must have violently redirected it. The leading theory points to a gravitational duel in the system's past. Another massive world, perhaps now ejected into the darkness, could have gravitationally slung HTP 7b into its bizarre, reversed orbit. Another possibility involves the star's own gravitational influence on the protoplanetary disk, slowly dragging the planet inward and flipping its orbit over millions of years. This single world, moving against the current, tells a story of gravitational chaos. Its backward journey is a permanent scar, a record of a past instability so severe it turned a planet's path upside down. If you could stand on this world, its sun would rise in the west and set in the east, a constant, silent reminder of a cosmic battle fought long ago. How many other seemingly placid stars host planets carrying the hidden scars of such ancient turmoil? The chaos of backward orbits is one thing, but the weather on HD 80606b is something else entirely. This world does not have seasons. It has a single recurring cataclysm. Its orbit is not a gentle circle but a stretched, egg-shaped path that takes it on an incredible journey. For most of its 111-day year, it lingers in the frozen outer darkness, a frigid gas giant. But then, in a matter of just hours, it screams inward toward its star. It swings so close that the stellar radiation it receives increases by a factor of almost 1,000. The planet's day side, suddenly exposed to this inferno, superheats with shocking speed. Temperatures can skyrocket from hundreds of degrees below zero to well over 2,000 degrees Fahrenheit in less than a single Earth day. This is not a gradual warming. It is a planetary-scale thermal shock. The atmosphere cannot cope. The sudden, violent heating on one side of the planet creates a colossal pressure difference, launching supersonic winds that race to equalize the temperature. These are not ordinary storms, they are global tempests of unimaginable ferocity, shockwaves of hyperheated gas that rip across the entire world. If you could watch from a safe distance, you would see the planet literally glow as it approaches its star, its atmosphere boiling into a frenzy before your eyes. Then, just as quickly, it swings away, and the entire world begins the long, slow process of cooling back into its deep freeze. This planet lives a cycle of violent explosion and quiet hibernation over and over again. It is a world defined not by its average conditions, but by its most extreme moment. What would it be like to stand on a moon in that system, watching the primary world transform from an icy marble into a miniature sun and back again, all within a handful of hours? After a world of cataclysmic temperature swings, the universe offers a glimpse of perfect cosmic order. Orbiting a faint, ultra-cool dwarf star are 7 Earth-sized worlds, all moving in a breathtakingly precise gravitational dance. This is the TRAPPIST-1 system, a planetary family locked in orbital resonance. Their years are not random durations, they are mathematically perfect ratios of one another. For every 2 orbits the innermost planet completes, the second planet completes exactly 1. For every 3 orbits of the second, the third completes 2, and this chain of perfect fractions continues all the way out through the 7th and final world. This celestial harmony is not a coincidence, it is the signature of a profoundly calm and gentle birth. These planets did not form in violent collisions or chaotic migrations. They likely coalesced peacefully farther out from their star and then slowly, gracefully spiraled inward together, their gravitational nudges locking them into this stable, repeating pattern over millions of years. This resonant chain is so stable that it has likely persisted for billions of years, a cosmic melody playing on an unimaginable timescale. If you could stand on one of these worlds, you would witness a sky filled with neighboring planets, some appearing larger than our own moon. Their predictable, rhythmic passes a constant reminder of the system's deep and abiding order. The existence of such perfect harmony challenges the narrative of a violent cosmos, proving that some stellar families can achieve a state of near-permanent peace. What could life become on a world where the heavens themselves move to such a perfect, predictable clock? This celestial harmony, however, cannot last forever. GJ 436b is a planet in the process of vanishing before our eyes. It is a Neptune-sized world locked in a death spiral so close to its red dwarf star that its atmosphere is being violently stripped away. The stellar radiation is so intense that it superheats the planet's hydrogen envelope, boiling it off into space. This creates a colossal, glowing tail of gas that streams behind the planet for millions of miles. From a distance, GJ 436b does not look like a traditional planet at all. It resembles a giant comet, a world being systematically dismantled by its own sun. This is not a slow geological process, it is an astronomical cataclysm happening in real time. Astronomers can actually measure the rate of mass loss, watching as this world slowly evaporates. The planet is losing billions of tons of its atmosphere every second, a relentless stellar wind tearing it apart atom by atom. What will be left when the destruction is complete? The most likely fate is a barren, rocky core, all that remains of a once mighty gas giant. This offers us a heartbreakingly rare opportunity. We are witnessing the final chapter in a planet's life cycle, a preview of what might eventually happen to many worlds, including our own, when their stars grow old and angry. GJ 436b is a living fossil of planetary death, a world sacrificing itself to teach us about the ultimate fate of all things in the cosmos. The serene glow of distant stars is a universal constant, but TRS-2b is a world that devours the light. This gas giant, orbiting perilously close to its star, holds the grim title of the darkest planet ever found. It is a blacker black than coal, darker than fresh asphalt, reflecting less than 1% of the light that falls upon it. If you could float near this world, you would be staring into an abyss, a featureless void in space that is somehow a planet. It absorbs almost all visible light, making it less reflective than black acrylic paint. How does a world become so profoundly dark? The answer is not a surface, but an atmosphere. Astronomers believe its upper air is a bizarre chemical brew, lacking the reflective clouds of ammonia that make Jupiter so bright. Instead, its atmosphere may be rich in vaporized sodium and potassium, or gaseous titanium oxide, substances that are voraciously efficient at absorbing light. These elements do not scatter or bounce photons back into space. They capture them, turning stellar radiation directly into heat and leaving almost nothing for our eyes to see. This creates a world of pure, searing darkness, its faint, dim red glow coming only from its own scorching heat, like a colossal ember drifting in the void. It is a planet that is almost a perfect optical illusion, a massive object that presents itself as a hole in the star field. What other cosmic secrets are hidden in plain sight, disguised by an absence of light, waiting for us to look not at what is shining but at what is not? This profound darkness gives way to a system of impossible light. HD 188,753 is not a single star, but a stellar trio engaged in a complex gravitational dance. And against all odds, a planet exists within this chaos. Imagine a world where your sky could be dominated by 3 different suns, casting multiple, shifting shadows throughout a single day. The primary star is a yellow sun similar to our own, with 2 smaller orange suns orbiting each other closely, and that pair swinging wildly around the main star. For a planet to form here, it had to survive in an environment of pure gravitational turmoil. Standard theory said planets could only coalesce in the quiet, stable disk around a single star. The competing gravity of multiple stars should tear apart the protoplanetary disk of dust and gas, preventing any world from ever taking shape, yet one did. This forces a complete rethink of planetary birth. Perhaps this world formed much farther out in a more stable region before migrating inward to its current precarious position. Or maybe the process of planet formation is far more robust and chaotic than we ever believed, able to occur even within a stellar hurricane. The very existence of this world proves that planets are not fussy about their neighborhoods. They can arise in the most crowded and unstable of cosmic cities, thriving where we thought it was impossible. What would a sunset look like with 3 stars dipping below the horizon at different times, painting the sky in a symphony of colors? This triple sun system expands the frontier of the habitable, suggesting that even in the most crowded stellar systems, a world might find a way to call the light its home. There is a world that has witnessed nearly the entire history of the cosmos. Orbiting the faint, dense corpses of 2 dead stars, a pulsar and a white dwarf, lies PSRB 1620-26b, a planet known as Methuselah. This gas giant is not merely old, it is ancient, an elder of the galaxy at nearly 13 billion years of age. It formed when the universe itself was in its cosmic infancy, just 1 billion years after the Big Bang. To put that in perspective, this planet is more than 2.5 times older than our Earth. It has existed for almost as long as time and matter have been woven together. How could a planet survive in such a violent stellar graveyard? Its story is one of apocalyptic endurance. Astronomers believe Methuselah first formed around a normal, sun-like star. That star eventually died in a colossal supernova explosion, an event that should have utterly annihilated any orbiting worlds, yet somehow this planet persisted. The supernova's fury may have transformed it, blasting away its atmosphere and leaving behind a scorched, dense core. Later, the system was captured by the binary pair of stellar remnants it now calls home. It now orbits this ghostly couple every 100 years, a silent testament to resilience. This world is a living fossil from the dawn of galactic creation. It proves that planets began forming almost as soon as the first stars ignited, and that some are tough enough to outlive their suns not just once but twice. What secrets about the very first chapters of star birth are locked within its ancient, enduring presence? There is a world where the sky bleeds molten metal. WASP 76b is an ultra-hot Jupiter where the concept of weather reaches a terrifying new extreme. This planet is tidally locked, meaning one side is permanently scorched by its star while the other is trapped in endless night. The temperature difference is staggering. The day side heats to nearly 4,000 degrees Fahrenheit, a furnace so intense that metals like iron do not just melt on the surface. They vaporize, turning into a gaseous mist that rises into the upper atmosphere. But the story does not end there. Howling winds, born from the immense pressure difference between the inferno and the freezer, carry this vaporized iron across the twilight terminator to the frigid night side. Here, temperatures plummet by over 1,000 degrees. In the sudden, profound cold of that permanent shadow, the iron vapor can no longer remain a gas. It condenses, it coalesces into droplets, and then it falls. The night side of WASP 76b experiences a perpetual, global shower of liquid iron, a rain of pure metal sleeting down from a black sky. Imagine standing on that dark surface, looking up at a sky not with clouds of water, but with clouds of glowing, vaporized iron, ready to unleash a storm of incandescent droplets. This is not a weather cycle of evaporation and precipitation as we know it. It is a planetary scale foundry, a brutal demonstration of how a star's relentless energy can twist the very elements into a form of atmospheric torture. What other precious or deadly elements could be swept up in such a terrifying cycle on worlds we have yet to find? The violence of planetary weather is a local phenomenon, but the architecture of entire systems is shaped by subtler, more persistent forces. Far closer to home within our own solar system, a miniature model of cosmic construction is on display. Saturn's magnificent rings are not a static, frozen sculpture. They are a dynamic arena constantly being shaped and sculpted by tiny, hidden architects. Small moons like Daphne's and Pan, no larger than a few dozen miles across, orbit within the rings themselves. Their gentle but persistent gravity acts as celestial shepherds, carving out pristine gaps and sculpting magnificent waves in the icy particles around them. As Daphne's travels along its path, its gravitational pull kicks particles away from its immediate vicinity, clearing the Keeler gap, but its influence does not stop at the edge. It also tugs on the particles just outside the gap, creating a rippling wave pattern that moves through the rings like a wake following a boat on a still lake. We can see this process happening in real time, a perfect, observable demonstration of how gravity clears a path. This is not just a beautiful sight. It is a fundamental lesson in planetary formation. These shepherding moons are a scaled-down version of what happens on a colossal scale in infant solar systems. A young, growing planet does not simply sweep up all the material in its path through collisions. Its gravity creates order out of chaos, pushing smaller debris away, clearing its orbital lane, and leaving behind a clean, defined path around its star. The gaps in Saturn's rings are a direct, visible echo of that planet-building process. They show us that even the smallest worlds can exert profound control over their environment, writing their history in the language of gravity and motion. What other subtle, unseen forces are currently at work in distant star systems, carving out the futures of worlds we have only just begun to discover? Shepherding moons sculpting icy rings is a delicate art, but some worlds are so light they seem to defy the very idea of substance. Circling the young star Kepler 51 are three ghostly giants known as super puffs. These planets are cosmic marvels, each one nearly the size of Jupiter, yet possessing less than 1% of its mass. Their density is so astonishingly low it is comparable to cotton candy. If you could build a bathtub large enough to hold one, it would float without a second thought. how can a planet exist as a fleeting wisp, a giant balloon of a world? The answer is not solid ground, but an immense bloated atmosphere. These are not gas giants in the traditional sense. They are more like colossal clouds of hydrogen and helium, held together by a weak gravitational pull and inflated to staggering proportions. Astronomers believe their extreme puffiness is a youthful phase. The star system is only a few 100 million years old, and the planets are still cooling from their violent births. This internal heat, combined with the intense radiation from their star, keeps their atmospheres hot and expanded, like a freshly baked soufflé that has not yet had time to settle. The true puzzle is what lies at their core. Do they have a small, dense heart of rock and ice, or are they composed almost entirely of these light gases with no substantial center at all? These superpuffs challenge our most basic classifications, existing in a category all their own between planet and cloud. They are a temporary spectacle in the cosmos, destined to eventually cool, contract, and lose their magnificent fluffiness over billions of years. What other fleeting, ethereal wonders exist in the universe? Beautiful anomalies that appear only for a cosmic moment before fading into a more ordinary state. K2-22b is a world actively turning to dust before our telescopes. This rocky body, smaller than Earth, orbits its dim red dwarf star so closely that a full year passes in just 9 hours. Such proximity places it in an unbearable stellar furnace, where surface temperatures are thought to approach 2,000 degrees Fahrenheit. This relentless heat is literally cooking the planet from the outside in, vaporizing its very rock and minerals. But the destruction does not stop there. The planet's surface is not simply melting. It is being blasted into space, creating a colossal, trailing cloud of fine dust and debris that stretches for hundreds of thousands of miles. Astronomers first detected this world not by the steady shadow of a solid globe, but by the wildly fluctuating dimming of its star, a telltale signature of a disintegrating object and its enormous, dusty shroud. This is not a theoretical end state. We are witnessing the final death throes of a planet in real time, a world being systematically vaporized by its own sun. The physics at work are as brutal as they are simple. The intense stellar radiation is so powerful that it overcomes the planet's gravity, lifting material directly from the surface and hurling it into the void. This process is likely creating a long, comet-like tail of destruction that streams behind the planet on its frantic orbital path. Each pass by the star strips away another layer, another million tons of its substance, gradually erasing it from existence. What will remain when the destruction is complete? Perhaps only a barren, scorched cinder of a core, or maybe nothing at all. K2-22b offers a heartbreakingly transient glimpse into a planetary extinction event, a stark reminder that even worlds of solid rock are not permanent in the face of a star's fury. A planet with 2 suns is no longer just science fiction. Kepler-16b is a cold, Saturn-sized world that proved a galaxy far, far away could exist right here in our own. It was the first confirmed planet found orbiting a binary star system, a pair of stars that dance around a shared center of gravity. This real-world Tatooine orbits both stars, completing a full circuit in about 229 days. Its twin suns are smaller and cooler than our own, one an orange star and the other a red dwarf, locked in a 41-day orbital embrace. From the surface of this gas giant, you would see 2 distinct sunrises and 2 sunsets, casting complex, shifting shadows across the sky. The orbital mechanics here are a delicate ballet. The planet follows a wide, stable path around the center of mass of both stars. This forces the 2 stars to orbit much closer to each other, creating a gravitational environment that is surprisingly orderly. The existence of a stable planet here shattered previous assumptions that such a system would be too chaotic for a world to form or maintain a stable orbit. It proved that planetary formation is robust enough to occur even within the complex gravity of 2 stars. This discovery also expanded our understanding of habitable zones. In a binary system, the region where liquid water could exist is not a simple ring. It is shaped by the combined light and heat of both stars, creating a potentially wider and more dynamic band of possibility. While Kepler 16b itself is a frigid giant, its very existence opens the door to the possibility of rocky, Earth-like worlds in similar double star systems, worlds where a double sunset is not a cinematic fantasy but a daily celestial event. How many other such worlds are waiting in the twilight of twin stars, their skies painted with the light of two different suns? Beneath the gentle glow of a distant star, a world exists without a single mountain peak or continent to break its surface. This is Oceanus, the ultimate water world, a theoretical planet cloaked in a global ocean hundreds of kilometers deep. The sheer scale of this sea is almost incomprehensible. If you were to drop the deepest point of Earth's Mariana Trench into it, it would vanish without a trace, lost in an abyss of liquid that stretches from pole to pole. The pressure at the bottom of this alien ocean would be millions of times greater than anything in our own seas, creating conditions so extreme that the water itself transforms. It cannot remain a simple liquid. At those staggering depths, the water molecules are forced into a crystalline structure, not because of cold, but because of the crushing weight. This creates exotic forms of ice with names like Ice 6 and Ice 7 that are denser than liquid water and form at temperatures that would boil a kettle on Earth. This is not the ice we know. It is a hot, solid ice that forms a bizarre seabed, a rigid floor at the bottom of a planet-wide ocean. There would be no gentle sandy slopes or volcanic vents as we imagine them. The entire base of this world would be a single, unbroken plain of superheated crystalline ice. How could life emerge in such an environment? Any potential biological processes would be confined to the upper, more temperate layers of the ocean, forever isolated from the solid core of the planet by an impassable barrier of hot, solid water. Oceanus presents a vision of a world that is both utterly familiar and profoundly alien, a testament to how the most common substance in the universe can be forged into landscapes beyond our wildest dreams. Some worlds are not merely drifting in the dark, they are fleeing it at impossible speeds. These are the hypervelocity planets, rogue worlds transformed into cosmic bullets. They do not wander, they scream across the galaxy, ejected from their home systems by the most powerful slingshot in the universe, gravity itself. The most likely culprit is a close encounter with a supermassive black hole at the galactic center. When a binary star system ventures too close to this gravitational monster, one star can be captured while the other is violently flung away at millions of miles per hour. Any planets orbiting that ejected star are ripped from their celestial moorings and carried along for the ride. Another scenario involves a gravitational kick from a giant planet within a system, a chaotic interaction so severe it launches a smaller world outward with enough force to escape its star's grasp entirely. These are not the slow, cold rogues we first encountered. They are projectiles carrying the kinetic energy of their traumatic birth across the light years. Their surfaces would be frozen wastelands, their stars just a receding point of light in an ever-darkening sky. What would it be like to stand on such a world, watching the entire galaxy slowly recede as you travel into the absolute emptiness between galaxies? These hypervelocity exiles prove that the cosmos is not just a place of creation, but also of expulsion, where a world's entire destiny can be rewritten in a single, violent moment. How many of these nomadic worlds are now crossing the Great Void, their origins a mystery sealed by velocity and distance? A shadow fell across a distant star, but this was no ordinary eclipse. The light did not dim with the clean, smooth curve of a planet passing by. It flickered. It plunged into deep valleys of darkness and then climbed back out in jagged, uneven steps. This was the signature of J1407b, a world that may be the most spectacular ringed planet in the galaxy. its hypothetical ring system is not merely large. It is colossal, stretching over a distance nearly 200 times wider than Saturn's magnificent belts. If you were to place this super Saturn in our own solar system, its rings would dominate the sky, extending far beyond the orbit of our Sun. They would appear larger than a full moon, a breathtaking, impossible bridge of ice and dust arching across the heavens. But the true mystery is not just their scale. It is their tilt. This entire gargantuan disk is inclined, orbiting at a sharp angle to our line of sight. As the planet and its rings transit its star, they do not present a single, solid barrier. Instead, the tilted rings sweep across the stellar face, their complex structure of gaps, bands, and dense clumps casting a constantly shifting, intricate pattern of shadows. The star's light winks in and out as it passes behind different parts of the ring system, creating a light curve of staggering complexity. This is not a simple on-off switch. It is a celestial symphony of shadows, and within those shadows, astronomers see hints of something even more extraordinary. Deep within the rings, there appear to be sharp, clean gaps. These are not random voids. They are the hallmarks of shepherding moons, tiny worlds in the act of being born. Their gravity is clearing their orbital paths, sweeping the ring material aside, just as Daphne's carves its path through Saturn's rings. We may be witnessing the real-time formation of an entire lunar system. The dramatic eclipses of J1407b are more than just a light show. They are a blueprint, a detailed map of a planetary nursery on a scale we once thought impossible. What other colossal architectures are waiting to be decoded from the flickering of other stars, each one a story written in shadow and light? WASP-12b is not just being consumed, it is a world with a sky made of poison. This hot Jupiter orbits so close to its star that it is being stretched into an egg shape, its atmosphere actively siphoned away in a death spiral. Yet its true strangeness lies not in its destruction, but in its composition. Astronomers analyzing the light filtering through its air found an atmosphere almost completely devoid of water. Instead, it is choked with carbon, possessing a carbon-to-oxygen ratio greater than 1. This single measurement transforms the entire world. On Earth, with an abundance of oxygen, carbon binds with it to form gases like carbon dioxide. But on a world where carbon is the dominant element, the chemistry is turned upside down. Without ample oxygen to bond with, the carbon is free to form other structures. The intense heat and pressure deep within the planet could forge that carbon into layers of diamond. The crushing weight could compress it into vast fields of graphite. This suggests a geology we can scarcely picture. Instead of silicate rock mountains, this world could have peaks of pure diamond and shorelines of graphite sand. Imagine a landscape where the very ground beneath your feet is a precious gem, a treasure trove rendered worthless by its sheer, terrifying abundance. The planet's atmosphere might even be filled with a haze of soot, a perpetual, dark smog raining tiny diamonds into its molten interior. WASP-12b presents a chilling paradox. It is a world of immense, impossible wealth, being systematically torn apart and devoured by its star. What does it mean for a planet to be made of the very stuff we value so highly, only to exist as a monument to its own ephemeral, catastrophic end? HD 209458b was the first world to reveal its own destruction. Astronomers call it Osiris, and it holds a grim title as the first exoplanet ever caught losing its atmosphere. This gas giant orbits so close to its star that the searing heat boils its hydrogen envelope into space, creating a vast, comet-like tail of glowing gas. But the planet's atmosphere held another secret, one that required a different kind of observation to uncover. By analyzing the subtle shift in the star's light as it filtered through the planet's outer layers, scientists did something astonishing. They measured the weather. They discovered that supersonic winds howling at thousands of miles per hour race from the scorching day side to the cooler night side. These are not gentle breezes, they are a planetary-scale furnace blast, so powerful they carry vaporized metals and silicates across the Terminator line. On the night side, these materials likely condense into tiny droplets, creating clouds of molten rock and metal that rain back into the deeper atmosphere. Imagine a world where the wind itself is a scalding river of vaporized rock, a permanent hurricane of elemental fury. This discovery of atmospheric motion on a world so far away was a monumental leap. It transformed exoplanets from distant points of light into dynamic, breathing worlds with their own violent meteorology. It proved that we could not only find these worlds, but also listen to the stories written in their raging storms. What other climate systems of unimaginable ferocity are waiting for us to decode their violent, alien rhythms? This gravitational melody found in TRAPPIST-1 is not the only symphony in the cosmos. A far more complex composition plays out in the Kepler-223 system, where 4 planets are locked in an intricate 4-body resonance. Their orbits are not just paired in simple ratios. They are all linked together in a precise, repeating chain. For every 3 orbits the innermost planet completes, the second planet completes exactly 2. For every 4 orbits of the second, the third completes 3, and for every 2 orbits of the third, the outermost completes 1. This is not a random coincidence. It is a gravitational clockwork of breathtaking precision, a celestial rhythm that has ticked reliably for billions of years. This rare multi-world resonance acts as a living fossil, a perfect snapshot of the system's earliest days. How could such a delicate arrangement possibly form and survive? The answer lies in a gentle planetary migration. Astronomers believe these 4 giants did not form in their current tight orbits. They were born farther out in the protoplanetary disk and then, over eons, spiraled inward together. As they migrated, their gravitational nudges gently pushed and pulled on one another, their rhythms synchronizing until they fell into this stable, resonant lock. The persistence of this chain is a testament to an unusually peaceful history. It tells us that no violent intruders have disrupted this cosmic ballet, no gravitational shocks have thrown its timing off. The system has been a quiet sanctuary, allowing this delicate dance to continue since the dawn of planetary time. If you could listen to the gravitational waves emanating from Kepler-223, you would hear a perfect, repeating chord, a harmony forged in the system's infancy and preserved against the chaos of the galaxy. What other ancient, rhythmic patterns are waiting to be heard, each one a silent record of a solar system's gentle birth? The gentle clockwork of orbital resonance is replaced by a world leaking its very essence into the void. HTP-11b is a Neptune-sized world caught in the act of a profound transformation, its atmosphere bleeding away in a giant plume. The escaping element is not hydrogen, the most common gas in the universe, but helium. This was the first time helium was ever detected in the air of a world beyond our solar system, a discovery that changed how we see atmospheric escape. On most exoplanets, the telltale sign of a dying atmosphere is hydrogen, a light gas easily boiled off by a star's heat, but helium is heavier, more stubborn. To see it flowing away in such a massive tail means the processes tearing this world apart are more powerful and complex than we knew. The star's intense radiation is not just heating the atmosphere. It is inflating it, causing the helium-rich layers to puff up and expand far beyond the planet's gravitational grasp. This creates a comet-like envelope that stellar winds then blow back into a vast, streaming tail. It is a slower, more deliberate form of evaporation than the violent stripping seen on other worlds. Think of a dandelion clock slowly shedding its seeds in a gentle breeze, each wisp of helium carrying away a piece of the planet's history. This helium signature is a new tool for astronomers. It allows us to peer deeper into the atmospheric dynamics of these distant worlds, to understand not just that they are fading, but precisely how. The Great Escape of HDP 11b reveals that planetary death comes in many forms, some violent and swift, others a quiet, persistent sigh into the eternal night. What other heavy elements are silently streaming from seemingly stable worlds, gradually transforming them into something entirely new over the eons? A planet does not always need to orbit alone. In the complex gravitational dance around a star, there exist points of perfect equilibrium, celestial parking spots where the pull of the star and the tug of an orbiting planet precisely balance out. These are the Lagrange points, and at two of them, 60 degrees ahead and behind a world in its orbit, the conditions are stable enough to trap other objects for billions of years. We see this in our own solar system with Jupiter, which is accompanied by swarms of Trojan asteroids sharing its path around the Sun. But this leads to a staggering theoretical possibility. Could a planet, an entire world, share its orbit with another planet in this way? Could there be Trojan planets, two Earth-sized worlds or even larger, eternally separated by that 60-degree arc, forever chasing or leading each other around their star without ever drawing closer? This is not a configuration we have yet confirmed, but the physics suggests it is perfectly plausible. The gravitational sweet spots at the L4 and L5 Lagrange points are remarkably stable. An object placed there will oscillate gently around that point, held in a graceful, looping path relative to the larger planet. The primary requirement is a significant mass difference between the star and the guiding planet, a condition easily met by a Jupiter-like world. Imagine a solar system where two gas giants, twins in size and composition, travel the same orbital highway. From the surface of a moon around one, you would see its sibling as a permanent, brilliant fixture in the sky, a second sun that never sets or rises but simply hangs in a fixed position, a constant companion in the heavens. The search for such a system is incredibly difficult. The telltale wobble in a star's motion or the dimming of its light from a transit would be subtle and complex, as two massive worlds influence each other within the same orbital period. Finding a Trojan planet would be a monumental discovery, proving that planets can be born as siblings, not just neighbors, and that the most stable arrangements in the universe can be far more complex and beautiful than we ever dreamed. What other cosmic partnerships are hiding in the gravitational harmony of distant stars, waiting to be found? Kepler 78b is a world where a single day lasts longer than its entire year. This scorched sphere completes a full orbit around its star in just 8.5 hours, a frantic dance that leaves its surface glowing at 2,000 degrees Celsius. That is hot enough to vaporize granite, turning the entire landscape into a global ocean of molten lava. There is no solid ground, only a perpetual, seething sea of liquid rock under a blistering, white-hot sky. The planet is physically touching the outer limits of its star's fiery envelope, a proximity so extreme it defies all conventional models of planetary formation. How did it get there? A world of this size, with a density similar to Earth, could not have formed in its current location. The protoplanetary disk of dust and gas from which planets are born would have been far too hot and sparse so close to the newborn star. The raw materials for a rocky world simply could not have coalesced there. This means Kepler 78b must have migrated inward from a much more distant birthplace. But the journey it took remains one of the greatest puzzles in planetary science. Did it spiral inward slowly, dragged through the primordial disk by gravitational interactions, a process that should have taken millions of years and ended with the planet plunging into the star? Or was it violently hurled into this suicidal orbit by a gravitational slingshot from another, more massive world in a chaotic, long-forgotten celestial encounter? This tiny, blazing world is a paradox, a planet living on the very edge of oblivion, challenging us to understand the most dramatic and violent journeys a world can ever take. What does its impossible existence tell us about the turbulent youth of other, solar systems and the unseen migrations that shaped their final arrangements? Even the cradles of planets are not always safe. Recent observations of young, still-forming star systems reveal a startling truth. The protoplanetary disks, those vast, flat rings of dust and gas where worlds are born, are sometimes profoundly warped. They are not the pristine, dinner plate-shaped nurseries we once envisioned. Instead, some are tilted, twisted, or bent into a pretzel shape, their orderly structure broken by some invisible hand. This distortion is a clear sign of an intruder, a gravitational vandal that has passed through the stellar neighborhood. A wandering star drifting too close could have exerted a powerful tidal force, pulling and twisting the entire disk out of alignment. The consequences of this cosmic trespass are immense. Within a warped disk, the process of planet formation is thrown into chaos. The dust grains that must gently collide to build pebbles, then rocks, then planets, now find themselves on chaotic, intersecting paths. The delicate gravitational dance that leads to orderly orbits is shattered before it can even begin. A system born from such a warped disk would be destined for a lifetime of instability, its planets likely following tilted, eccentric paths, much like the chaotic worlds of Upsilon Andromeda. This discovery forces us to reconsider the very environment of stellar birth. Most stars are born in dense clusters surrounded by siblings. In such a crowded nursery, close encounters may not be the exception but the rule. Our own solar system, with its planets orbiting in a neat, flat plane, might be the product of an unusually quiet and isolated childhood. How many other planetary families had their original blueprints permanently scarred by a passing star's gravity, their futures warped before their first worlds even finished forming? Gliese 436b holds a secret beneath its boiling hydrogen atmosphere. This Neptune-sized world orbits so close to its star that its surface temperature soars to over 800 degrees Fahrenheit, a heat that should vaporize water instantly. Yet the planet's mass and density reveal a profound paradox. Deep within its core, under thousands of miles of scorching gas, lies a heart of solid ice. This is not the ice of our frozen lakes. It is a substance forged by pure pressure, a crystalline form of water known as Ice 7. At pressures over 1,000,000 times greater than Earth's atmosphere, water molecules are squeezed into a rigid, cubic lattice structure. The incredible weight of the planet's own atmosphere creates a crushing grip, forcing the water into this solid state despite the blistering heat. Imagine a world where an ocean of superheated steam is held aloft by a bedrock of scalding, solid ice. This hot ice is denser than liquid water, forming a stable foundation that never melts. The planet becomes a layered enigma, a fiery gas giant cloaking a frozen, crystalline interior. How can such opposing extremes coexist? Gliese 436b defies our everyday experience, proving that pressure can triumph over temperature, creating landscapes where the very definitions of solid and liquid lose all meaning. What other impossible materials are hiding inside the countless worlds drifting in the galaxy, waiting for the right conditions to reveal their true, alien nature? The orderly spin of a solar system can be a fragile thing, a truth made violently clear by Kepler 56. Here, the star itself has been knocked askew, its axis of rotation tilted dramatically compared to the flat plane in which its planets orbit. The entire system is fundamentally misaligned, as if the central sun was clumsily re-glued into place by a giant hand. This is not a simple case of a single rebellious planet. This is a star that has lost its bearing, and the key to this cosmic whiplash lies in the distant dark. Orbiting far beyond the known planets is a massive, unseen companion, another star whose gravity has been slowly, relentlessly pulling on the entire system. Over billions of years, this distant tug-of-war has torqued the central star, forcing its spin axis to gradually process or wobble out of alignment with its planetary family. The planets continue their stately dance in their original flat disk, oblivious to the fact that their parent star is now spinning on its side relative to their paths. If you could stand on one of these worlds, the star would not follow a simple arc across the sky. Its path would trace a more complex loop over the course of a year, a permanent celestial anomaly written in the daylight. This discovery reveals that the gravitational influence of a stellar sibling can reach deep into a system's heart, warping its very core long after the planets have formed. How many other seemingly normal stars are secretly tilted, their silent wobble a ghostly record of an invisible dance with a distant companion? The silent gravitational vandal that warps a young system leaves behind a calling card of dust. For decades, one of the most brilliant clues to this process was not a planet but a disk. The young star Beta Pictoris is surrounded by a vast, flat plain of gas, dust, and countless icy comets, a sight so bright it could be seen directly from Earth. This was the protoplanetary disk made visible, a snapshot of a solar system under construction, but the image held a strange distortion. The entire disk was not perfectly flat. It displayed a distinct warp, a subtle kink in its structure, as if a heavy object were tugging on it from within. This was the first powerful hint. Astronomers proposed that the warp was the gravitational signature of an unseen world, a massive planet orbiting just off the disk's plane, its gravity pulling and twisting the surrounding dust like a hidden hand stirring a pot of glitter. For years, this dusty disk was the only evidence, a ghostly fingerprint pointing toward an invisible giant. Then the confirmation came. Advanced telescopes directly imaged the planet itself, Beta Pictoris b, a young gas giant several times the mass of Jupiter, orbiting right within that warped region of the disk. The prediction made from observing a twist in a cloud of dust had proven stunningly accurate. This sequence of discovery, from indirect clue to direct confirmation, became a blueprint for the entire field of exoplanet science. It taught us to read the subtle signs written in the raw materials of star systems, to see the invisible hands of planets sculpting their environments long before our cameras were powerful enough to see the worlds themselves. How many other dusty disks glowing around distant stars hold the hidden blueprints for entire families of planets we have not yet seen? A gas giant named Kelt 4ab offers a masterclass in celestial hierarchy. This hot Jupiter orbits a single sun-like star so closely that its year lasts a mere 3 days. Yet that star is not alone. It is the primary member of a triple star system, with 2 smaller, fainter stars locked in a tight binary dance with each other, and that pair slowly pirouetting around the primary star and its planet. From the cloud tops of this bloated world, the sky presents an extraordinary spectacle. Its primary sun would dominate the heavens, a vast, brilliant disk. But the distant binary pair would also be visible, appearing as 2 incredibly bright stars, shining with a combined light several thousand times brighter than our full moon. They would be close enough in the sky to be seen simultaneously in daylight, a constant, dazzling reminder of the system's complex architecture. How did this planet form in such a gravitational whirlpool? Its existence suggests it was born much farther out, in a more stable region of the protoplanetary disk, before migrating inward to its current scorching orbit. The fact that it survived this journey without being ejected by the competing gravitational tugs of 3 different stars is a testament to the surprising stability that can emerge from chaos. This world proves that planets can not only form in multi-star systems, but they can also find a stable, if dramatic, home within them. What other intricate stellar families are out there, with planets serving as the calm center of a gravitational storm? The silent, steady rhythm of a planet's orbit is not always a permanent thing. For the gas giant WASP 43b, its path around its star is a countdown to oblivion. This world is slowly, inexorably spiraling inward, dragged down by the gravitational tides raised by its own sun. Astronomers have measured this decay with stunning precision, watching as the planet's orbital period shrinks by a fraction of a second each year. It may seem like a trivial amount, but over millions of years, this constant loss of energy adds up, pulling the planet on an inescapable collision course. The process is driven by a simple, brutal physics. Just as our moon's gravity tugs on Earth's oceans, creating the tides, the star's immense gravity pulls on the planet, distorting its shape. This tidal friction saps the planet's orbital energy, bleeding its momentum away and causing it to fall ever closer. We are witnessing the long-term fate of any world that dares to orbit too near its stellar parent. What does this mean for the countless other hot Jupiters we have discovered? Many of them may be on similar, slow-motion death marches, their seemingly stable orbits merely a temporary pause before the final plunge. WASP-43b offers us a rare and precious timeline, a chance to understand not just how planets live, but how they die. How many other celestial clocks are ticking down across the galaxy, their final moments written in the silent mathematics of gravity. The color of a gas giant can be a lie. GJ504b glows with a soft cherry blossom pink, a gentle hue that belies the violent turmoil within its atmosphere. This world, one of the few planets ever directly photographed, is a beautiful enigma. It orbits at a vast distance from its sun-like star, a separation so great it challenges our understanding of how giant planets form. But its true mystery is not its orbit nor its charming color. It is what is missing from its air. When astronomers analyzed the light shimmering from this pink giant, they found a shocking deficiency. Its atmosphere holds almost no methane. For a gas giant, this is like finding an ocean without salt. In our own solar system, Jupiter and Saturn are rich with methane, a fundamental molecule that forms readily in the cold, dense conditions of a gas giant's interior. Its absence on GJ504b points to a profound atmospheric rebellion. One possibility is a process called vertical mixing. Imagine a planetary atmosphere not as a calm, layered blanket, but as a boiling pot of soup. Powerful, turbulent updrafts from the deep, hot interior could be dragging the planet's chemistry upward at a ferocious rate. The methane molecules are ripped from their stable, cold environment and thrust into the searing upper atmosphere, where they are literally torn apart by the intense stellar radiation before our telescopes can even detect them. Another, even stranger idea is non-equilibrium chemistry. The atmosphere may be host to violent reactions that are continuously destroying the methane faster than it can be replenished, a permanent chemical war raging in the pink clouds. This single, missing ingredient forces us to see gas giants not as predictable spheres of hydrogen and helium, but as dynamic chemical laboratories, each one following its own unique recipe for atmospheric chaos. What other fundamental rules of planetary science are being broken on worlds whose gentle colors mask the storms within? The vastness of a binary star system is not a barrier to giant worlds. Kepler-1647b is a colossal circumbinary planet, a Jupiter-sized giant that orbits not one, but two stars in a wide, stable dance. This is the largest known planet of its kind, a true titan in a double sun system. Its orbit is measured not in days, but in years, taking over 1,100 Earth days to complete a single circuit around its stellar pair. This long, graceful path places it squarely within the system's habitable zone, that precious region where temperatures could allow for liquid water to exist. Yet this world itself is almost certainly a gas giant, a swirling ball of hydrogen and helium with no solid surface to walk upon. Its significance is not as a potential home for life, but as a profound proof of concept. The existence of such a large, long-period planet in a binary system was once thought to be nearly impossible. The competing gravitational tugs from two stars should, in theory, disrupt the slow, gentle accumulation of material needed to build a gas giant so far out, or else destabilize its orbit over time. Kepler-1647b defies that expectation. It demonstrates that planetary formation is a robust and versatile process, capable of assembling massive worlds even in the complex gravitational environment of a binary star. This giant did not just form, it has persisted, its wide orbit a sanctuary of stability amidst the stellar dance. Its presence opens up a new realm of possibility, suggesting that where a gas giant can find a stable home, so too could rocky moons with the right conditions. What other gentle giants are circling twin suns in the galactic quiet? Their vast orbits tracing paths of gravitational perfection we are only beginning to understand. The serene, deep blue marble of HD 189,733b is an illusion. This distant hot Jupiter appears as a tranquil cobalt sphere, a hue created by a hazy atmosphere that scatters blue light. But the reality is a world of unimaginable ferocity. The Hubble Space Telescope peered into that beautiful blue shroud and found a signature of silicate, the mineral that makes up sand and glass on Earth. Here, however, those silicates are not resting on a beach. They are suspended in the upper atmosphere as microscopic particles, a global haze of scorching dust. This finding alone painted a picture of a turbulent world, but the true violence was yet to be uncovered. Later observations revealed this planet is not just stormy, it is hemorrhaging. Its atmosphere is not leaking away in a steady stream, but is being blasted into space in sporadic, violent bursts. The star it orbits is an active red dwarf prone to sudden, enormous flares. When one of these stellar eruptions hits the planet, it acts like a cosmic blowtorch, superheating the atmosphere and literally boiling it away in great clouds. Imagine a world where the sky itself is periodically ripped away by the fury of its sun, a deep blue facade torn open to the void. This is not a slow, graceful evaporation. It is an atmospheric cataclysm that happens in fits and starts, a series of violent seizures that are stripping the world down to its core. How long can a planet endure such sporadic, brutal assaults before it is completely unmade? One face of Proxima Centauri b is forever scorched by its dim red sun, while the other is locked in an eternal, deep freeze. This Earth-sized world orbits within the habitable zone of our nearest stellar neighbor, but its potential for life is shaped by a fundamental constraint: tidal locking. The same gravitational forces that keep our moon showing only one face to Earth have permanently fixed this planet's rotation to its orbit around the faint star. The result is a world divided, a globe with a hemisphere of permanent day and a hemisphere of permanent night. On the day side, temperatures could be warm enough for liquid water to exist, but under the relentless glare of a sun that never sets. On the night side, the absence of any stellar heat would plunge temperatures to hundreds of degrees below zero, creating a frozen wasteland where the very air might snow out onto the ground. The true drama, however, unfolds in the twilight zone, the thin ribbon of territory between these two extremes. Here, the colossal temperature difference between the fiery day and the frigid night could power planets spanning weather systems. Hurricanes of unimaginable scale might rage, driven by the desperate attempt of the atmosphere to equalize the incredible heat imbalance. Superheated air from the day side would rush toward the freezing night side, while cold air from the dark side would flow back along the surface toward the light. Could life find a foothold in such a world? It would not be on the blistering day side or in the absolute dark. The most likely sanctuary is that perpetual twilight line where temperatures might be just right, and where the slow march of the Terminator offers a landscape of neither burning sun nor frozen night, but of eternal dusk. Any life here would be utterly alien, perhaps clinging to the ground in a world without sunrise or sunset, its entire existence defined by a single, unchangeable horizon. This world forces us to expand our definition of habitability beyond simple temperature, and to consider the strange, stable, and severe environments where biology might stubbornly take root. Kepler 79d drifts so lightly it seems to mock the very idea of a planet. It is one of those baffling super puffs, a world nearly the size of Neptune yet possessing barely more mass than Earth. This cosmic cotton candy presents a profound puzzle, its near weightless nature demanding an explanation. The leading theory suggests this is a world built not from rock but from an atmosphere. It may be a planet with a relatively small, dense core of rock and ice, utterly dwarfed and swaddled by an immense, puffed-up envelope of hydrogen and helium. This colossal shroud of lightweight gas, heated from within and bombarded by stellar radiation from without, expands to a staggering size, creating a planet that is more atmosphere than substance. It is a celestial hot air balloon, its vast exterior held aloft by the gentle push of internal warmth. But there is another, even more exotic possibility. Perhaps Kepler-79d is actively bleeding its own atmosphere into existence. Its core, still seething with heat from its violent formation, could be undergoing a process of intense outgassing. Imagine a planetary volcano on a global scale, where the very heart of the world is venting enormous quantities of light gases, constantly replenishing the immense, fluffy envelope and fighting against the natural tendency of gravity to compress it. This would make the planet a temporary phenomenon, a brilliant, inflated phase in its long life, destined to eventually deflate as its internal furnace cools and the outgassing slows to a stop. Whether a bloated gas giant or a world venting its own soul into space, Kepler-79d stands as a beautiful outlier, a whisper of a world that forces us to ask how many different ways a planet can simply hold itself together. The neat categories we use to classify celestial objects begin to crumble at HD 202,206. This system presents a cosmic puzzle, a strange hierarchy that defies simple labels. Here, a star is orbited by a heavy object roughly 17 times the mass of Jupiter. That object, in turn, is orbited by a more traditional planet. The middle object is the key to the mystery. It is far too massive to be a planet, yet it falls short of the mass needed to ignite hydrogen fusion and become a true star. This places it squarely in the category of a brown dwarf, a failed star. What we have, then, is not a simple star with planets, but a star with a binary companion, and that companion has its own planetary child. This configuration shatters the standard model of planetary formation. A planet is not supposed to form from the disk of a brown dwarf that is itself orbiting a star. The gravitational environment would be far too chaotic and violent for the gentle accumulation of dust and gas needed to build a stable world. The existence of this planetary system suggests a much more dramatic history. Perhaps the entire system was born from a single, unusually massive protoplanetary disk that fragmented, first forming the brown dwarf and then the smaller planet. Or maybe it is the result of a gravitational capture, where the star ensnared a wandering brown dwarf that already had its own planet in tow. Either scenario points to a birth filled with far more turbulence and complexity than we once assumed was typical. This strange celestial family forces us to ask a fundamental question. Where do we draw the line between a planet and a star when a world can orbit a failed sun that orbits a true one? The faint, cold glow around a distant star is more than just a cosmic smudge. It is the ghost of a solar system under construction, or the graveyard of one long past. These are debris disks, vast rings of dust, rock, and ice encircling other stars, the direct analogues of our own asteroid and Kuiper belts. When astronomers first detected these faint halos, they saw a simple confirmation that other stars had the same raw materials as our Sun. But the closer they looked, the more they realized these disks were not simple, uniform rings. They were sculpted. Many showed sharp inner edges, narrow gaps, and eccentric, lopsided shapes that natural particle dynamics could never create on their own. These were not the chaotic aftermath of planet formation. They were masterpieces of gravitational engineering, the only force capable of carving such intricate patterns into a disk of fine dust is the gravity of an unseen world. A planet orbiting within or just outside the disk acts as a celestial shepherd. Its persistent gravitational tug clears a path, pushing smaller debris away and creating a pristine gap in the ring. In other systems, a planet on a tilted orbit can drag the entire disk out of round, warping its structure into a lopsided ellipse. We see this process in miniature right here in our own solar system, where Saturn's moons sculpt its magnificent rings. On a colossal, interstellar scale, these warped and gapped debris disks are the blueprints left behind by invisible architects. They are the silent, spinning evidence of planets we cannot yet see directly, their presence announced only by the way they have brushed the dust of their birth environment. What other hidden worlds are writing their signatures in the faint, cold dust of their stellar homes, their entire existence inferred from the elegant emptiness they have carved out of the chaos? That faint, dim red glow in the telescope is not a single star, but a cosmic metropolis. Ultra-cool dwarf stars, the smallest and faintest of all, are turning out to be the galaxy's most prolific planetary factories. These diminutive stars, barely larger than Jupiter and thousands of times fainter than our Sun, are now known to host a staggering number of worlds with a strong preference for Earth-sized planets. Systems like TRAPPIST-1 with its 7 rocky bodies are not the exception for these stars. They are becoming the rule. How can such a tiny, cool star produce such a rich family of planets? The answer lies in its gentle nature. A star's mass directly influences the size of its protoplanetary disk, the raw material for planet building. While an ultra-cool dwarf has a smaller disk than a star like our Sun, the process is far more efficient. The material is packed into a tighter area, and the lower stellar mass makes it easier for smaller, rocky planets to coalesce and survive. There is simply less gravitational chaos to disrupt the delicate accretion of dust into pebbles and pebbles into worlds. Furthermore, the star's faintness creates a habitable zone that is incredibly close in. A planet must huddle near its star for warmth, but this proximity is not the death sentence it would be for a world orbiting a hotter star. At that short distance, the star's gravitational tides can lock the planet's rotation, creating a permanent dayside and nightside, but the gentle radiation allows for atmospheres to potentially persist. This combination of factors makes these faint red suns ideal nurseries for rocky, Earth-sized worlds. Their sheer abundance in the galaxy, far outnumbering stars like our Sun, suggests a profound possibility. The most common homes for planets in the Milky Way may not be around brilliant yellow suns, but in the quiet, crimson light of these ultra-cool dwarfs. If life is out there, it may not be basking under a sun like ours, but thriving in the perpetual twilight of a tiny red star, its sky dominated by a dozen neighboring worlds. The universe has a way of turning simple planets into atmospheric balloons. HTP 32b is a warm Jupiter, a gas giant that should be substantial, yet it has puffed itself up to an almost unbelievable size. Its radius is one of the most inflated ever measured, a vast, bloated sphere that defies the standard rules of planetary structure. This world is not just large, it is unnaturally distended, as if its very atmosphere is fighting against the pull of its own gravity. How does a planet become so profoundly inflated? The answer seems to lie not just in the heat from its star, but in a furnace burning deep within. One compelling theory points to the relentless pull of tidal forces. The planet's orbit may be subtly eccentric, not a perfect circle. As it travels this slightly oval path, the changing gravitational tug from its star constantly flexes the planet's interior. This perpetual stretching and squeezing generates immense friction, a tidal heating that acts like a built-in oven, pumping energy from the core outward and causing the entire gaseous envelope to expand. Another possibility is that the atmosphere itself is a master of energy absorption. Unusual chemicals high in its air may be acting like a perfect trap, soaking up stellar radiation and pushing that heat deep into the atmospheric layers, preventing it from escaping and forcing the planet to swell under the pressure. This world is a testament to hidden energies, a reminder that a planet's size is not always a simple matter of mass, but a complex balance between the fire from above and the furnace from within. What other inflated giants are drifting in the cosmos? Their true dimensions a silent record of the invisible forces warping them from the inside out. Our own solar system holds a hidden scar from its violent birth, a chemical frontier known as the Great Divide. This is not a physical gap in space, but a profound separation in the very ingredients that built our worlds. On one side of this invisible line, closer to the Sun, you find the rocky, terrestrial planets like Earth and Mars, worlds rich in silicate rock and metals. On the other side, beyond the asteroid belt, reside the gas and ice giants Jupiter and Saturn, composed mostly of hydrogen, helium, and frozen volatiles. For decades, this arrangement was simply the way things were. But now we understand this divide was engineered by the young Jupiter itself. As the giant planet formed, its immense gravity created a pressure barrier, a cosmic dam that prevented the dusty, rocky materials from the inner disk from mixing with the gaseous, icy materials from the outer disk. The infant solar system was effectively split into two distinct construction yards, each with its own raw materials. This discovery in our own backyard is now a revolutionary tool for understanding alien solar systems. When astronomers find a distant star system with both small, rocky worlds close in and giant, gassy worlds farther out, they can infer that a similar, ancient Great Divide was at work. It suggests a young, massive planet likely acted as a gravitational architect, partitioning the protoplanetary disk and dictating the final composition of every world that formed. This single concept transforms a random assortment of planets into a structured family, each member's identity shaped by its position relative to an invisible line drawn by a giant billions of years ago. How many other solar systems across the galaxy bear this same hidden signature, their own histories written in the segregated elements of their planets? This cosmic ambiguity forces us to confront a fundamental question. What exactly is the dividing line between a planet and a star? Brown dwarfs are the universe's ultimate in-between objects, celestial bodies that defy our neatest classifications. They form like stars, collapsing from vast clouds of gas and dust, but they never accumulate enough mass to cross the critical threshold. They are too small to ignite the sustained nuclear fusion of hydrogen in their cores, the process that makes a true star shine. A brown dwarf is born with a brief, faint internal fire, burning a heavy form of hydrogen called deuterium, but this fuel is scarce and quickly exhausted. After this short-lived flare of youth, the object simply cools and dims over billions of years, fading from a dull red ember to a cold, dark cinder. They are, in essence, failed stars. Yet, by mass, they overlap directly with the realm of planets. The smallest brown dwarfs are just a dozen times the mass of Jupiter, while the largest planets we have found are nearly that same size. So, is a brown dwarf a planet simply because it has a similar mass, or is it a star because it formed from a collapsing cloud? This is not just semantic quibbling. It strikes at the heart of how we understand the formation and nature of celestial bodies across the galaxy. The discovery of these ambiguous objects reveals a continuous spectrum between planets and stars, a gradual blending of categories that nature itself does not recognize. Our human need for clear labels meets its match in the messy, beautiful reality of the cosmos. What other fundamental definitions are we holding onto that the universe is quietly preparing to shatter? A gravitational clock ticks within the J876 system, its rhythm more complex than any we have yet encountered. Here, 4 planets are locked in an intricate celestial dance known as a Laplace resonance. This is not a simple 1-to-2 ratio. It is a chain of interlocking orbits, a gravitational pact that binds the fates of these worlds together. For every one orbit the innermost planet completes, the second completes exactly 2. For every 2 orbits of that second planet, the third completes 4, and this precise chain continues outward. They do not just orbit in harmony, they migrate in unison. As the system evolves over millions of years, these planets slowly spiral inward toward their star, their gravitational nudges ensuring they move as a single, coordinated unit, maintaining their perfect orbital ratios even as their paths change. This resonant migration is a fundamental clue to the quiet rearrangements that shape mature planetary systems. It reveals a gentle, collective journey, a far cry from the violent ejections and chaotic tilts seen elsewhere. The stability of this resonant chain acts as a protective mechanism, allowing an entire family of worlds to move through their solar system without crashing into one another. How many other systems have used this same gravitational music to safely orchestrate their own great migrations, finding order not in stillness but in synchronized motion? The violence of planetary formation is not the only force that can forge a hellscape. Some worlds are kept in a permanent state of geological fury by the relentless pull of their neighbors. Right here in our own solar system, orbiting Jupiter, is a masterclass in this process. The moon Io is a spectacle of pure fire, the most volcanically active body we have ever found. Its surface is a chaotic mosaic of yellow, red, and black, a map painted by hundreds of active volcanoes. Plumes of sulfur erupt dozens of miles into a thin sky, and vast lakes of molten lava shimmer across a landscape constantly being remade. Io should be a cold, dead rock, but it is kept in a perpetual furnace by an invisible force, tidal heating. As Io orbits Jupiter, the immense gravity of the giant planet pulls on the moon, stretching it. But Io is not alone in its orbit. The gravitational tugs from its sister moons, Europa and Ganymede, force it into a slightly elliptical path. This means Io's distance from Jupiter is always changing. The strength of the planetary pull varies, constantly flexing the moon's interior like a ball of clay being squeezed and released over and over. This friction generates colossal heat, melting Io's rocky interior into a global ocean of magma that then erupts violently through its crust. This is not a world with volcanoes, it is a volcano. Now, imagine this process scaled up to a planetary level. Picture a rocky exoplanet, an Io, orbiting dangerously close to its own hot Jupiter. The star's gravity would be immense, and the planet's orbit could be even more stretched and chaotic. The tidal heating would be far more extreme than anything Io experiences. Such a world would be a true vision of hell, with volcanic eruptions dwarfing anything in our solar system. Its entire surface a constantly churning cauldron of molten rock and superheated plumes. The very ground would be unstable, the atmosphere a toxic brew of volcanic gases, and the sky perpetually dark with ash. Could such a violent world ever be still? Or is it doomed to tear itself apart, its fiery heart stoked by the gravitational dance that defines its existence? The faint whisper of helium escaping a dying world opened a new chapter in exoplanet science. This element, the second most common in the universe, had long been a ghost in our atmospheric studies. Hydrogen was easy to spot, but helium is more reserved, its signal hidden in a very specific, hard-to-see part of the infrared spectrum. Then came a breakthrough. Astronomers realized that helium, when excited by a star's radiation, glows with a distinct and detectable signature. It creates a small, telltale dip in the star's light as the planet transits, a fingerprint we finally learned how to read. This new technique is like being given a universal key. Hydrogen escape can be masked by other processes, but helium is a clearer, more stable tracer. It allows us to peer into the atmospheres of smaller, cooler planets that were previously invisible to our methods. Suddenly, we are not just finding atmospheres. We are watching them bleed. We can measure the rate of escape, see the size and shape of the gas tails, and understand the relentless forces of stellar winds. A whole new population of worlds is now revealing its secrets, from puffy giants to rocky super-Earths. all through the silent, steady leak of a noble gas. What other fundamental truths about planetary life and death are written in this faint, infrared glow, waiting for us to learn their language? A star's death does not always mean the end for its planetary family. Around the white dwarf known as WD 1145+017, astronomers witnessed a solar system's final, agonizing act. They detected the subtle, repeating dimming of the dead star, a signature not of a clean transit but of a messy, chaotic one. The data revealed a collection of dusty, fragmented clouds crossing the star's face, all following the same orbital path. This was the debris trail of a small, rocky world being systematically torn apart. The white dwarf's immense gravity is so powerful that it exerts devastating tidal forces, stretching the object until its own structural integrity fails. This is not a gentle disintegration. It is a gravitational grinding, a relentless pull that rips asteroids and even planets apart, turning them into streams of dust and vapor that spiral down onto the surface of the dead star. For the first time, we had direct proof of active planetary destruction around a stellar corpse. This observation solves a long-standing mystery. White dwarfs often have atmospheres polluted with heavy elements like iron, calcium, and silicon, elements that should have sunk into their ultra-dense interiors billions of years ago. The only explanation was a recent infusion of rocky material. Now we know the source. The disintegrating body around WD 1145+017 is that source, a sacrificial world whose remains are currently raining down, polluting the white dwarf's pristine hydrogen atmosphere. This is the ultimate fate awaiting many inner solar systems. When a star like our Sun dies, it will swell into a red giant, likely consuming its inner planets before collapsing into a white dwarf. The surviving outer worlds and asteroid belts will then be thrown into gravitational chaos, their orbits destabilized. Many will be flung into the void, but some will be drawn inward, only to be shredded by the white dwarf's fierce gravity. We are watching the final consumption of a system's bones, a cosmic recycling project that writes the final chapter for worlds that once were. What other stellar graveyards are currently hosting these silent, destructive feasts, their light curves telling a story of ongoing celestial demolition? A moon could hold the key to life in a distant solar system. Our search for exoplanets is now expanding to include their satellites, a new frontier in the cosmic hunt. We call these worlds exomoons, and finding one would fundamentally reshape our understanding of where life could thrive. For years, our telescopes have been tuned to the rhythmic dimming of stars, revealing planets. But a moon, a smaller object orbiting a planet, is far more difficult to detect. Its signal is a whisper within a whisper, a tiny dip in starlight superimposed on the larger dip of its parent world. Yet the hunt is on because the potential reward is staggering. We need only look within our own solar system for inspiration. Europa, an icy moon of Jupiter, hides a global saltwater ocean beneath its frozen crust, an environment with more liquid water than all of Earth's oceans combined. Enceladus, a small moon of Saturn, spews geysers of water vapor and organic molecules into space from its own subsurface sea. These are not barren rocks. They are dynamic worlds kept warm and liquid not by the sun, but by the gravitational tug of war with their giant planets. This tidal heating can melt ice and power hydrothermal vents on the seafloor, environments that on Earth are teeming with life, entirely independent of sunlight. An exomoon orbiting a gas giant in its star's habitable zone would present a double chance for life. The planet could be a sterile giant, while its moon, warmed by both stellar light and planetary tides, could be a water-rich paradise. Imagine a world with multiple moons in its sky, one of them a vibrant blue and green, a sanctuary of biology in an otherwise empty system. The discovery of the first exomoon would prove that such complex, layered environments are not science fiction. It would tell us that the galaxy is not just filled with planets, but with entire planetary systems complete with families of moons, each one a potential world unto itself. How many of these hidden ocean worlds are waiting in the data, their presence not yet separated from the planets they call home? Deep within the chaotic heart of our galaxy, a new class of worlds defies the odds. The galactic bulge is a cosmic maelstrom, a densely packed sphere of ancient stars surrounding the supermassive black hole at the Milky Way's center. This is a region of extreme gravitational turbulence, bathed in intense radiation, where stellar collisions and close encounters are thought to be common. For a long time, astronomers assumed this violent environment would be a planetary dead zone, a place where the delicate process of planet formation simply could not succeed. The discovery of planets here was nothing short of a revolution. Using the subtle gravitational lensing effect known as microlensing, where a star's gravity acts as a magnifying glass for the light of a star behind it, astronomers detected the telltale signatures of worlds orbiting stars in this central bulge. These are not the young, placid worlds of the galactic suburbs. They are survivors forged in the galaxy's most extreme urban core. Their very existence proves that planet formation is not a delicate flower that only blooms in quiet stellar nurseries. It is a stubborn, tenacious weed that can take root almost anywhere, even in the fierce light and relentless gravity of the galactic downtown. How do these worlds endure? Their stars are typically ancient, population 2 stars, born when the universe was young and metal poor. Yet the bulge itself is paradoxically rich in heavier elements, forged in successive generations of stellar explosions. This suggests these planets may have formed later, from material enriched by the deaths of earlier stars, building their rocky cores in a second wave of cosmic construction. Finding planets here expands the possible real estate for worlds across the universe, suggesting that even the brightest, most crowded and chaotic regions of a galaxy could be dotted with ancient, hardy planets, silently orbiting in the perpetual glare of the galactic center. Our journey through these 50 strange and wonderful worlds reveals a cosmos of infinite variety. Each discovery rewrites our cosmic textbooks and expands the very definition of a planet. We have seen worlds of diamond and iron rain, planets lighter than cork and darker than coal, solar systems of perfect harmony and others of pure chaos. This astonishing diversity is not the exception, it is the rule. Our galaxy is a grand laboratory of physical extremes, where the familiar elements of rock, water, and gas are forged into landscapes that defy our wildest dreams. Every new world we find pushes the boundaries of what we thought was possible, forcing us to abandon our assumptions and embrace a universe that is far more creative than we are. The sheer strangeness of these distant systems is a profound message. It tells us that our own solar system, with its neat orbits and temperate worlds, is just one possible outcome in a near-infinite spectrum of planetary architectures. The search is far from over. With every new telescope and every fresh observation, we are not just adding to a list, we are learning a new language, the language of planetary formation and evolution, spoken in the silent, drifting orbs around other stars. The ultimate lesson of these 50 wonders is that we are only at the very beginning of understanding our place in this vast and spectacularly weird cosmos. So tell us, which of these 50 wonders left you in the greatest state of awe? Does the diamond super-Earth capture your imagination, or does the planet with a sky of molten iron redefine your idea of alien weather? Share your favorite strange discovery in the comments below. The universe is a library of endless mysteries, and our journey into its pages has only just begun. If you want to join the next cosmic adventure, make sure to like this video, subscribe to the channel, and tap the notification bell. The next discovery is always just one observation away.